Watch these steel pieces. They start moving before they touch the magnet. Nothing is pulling it with a string. The space around the magnet has changed. That changed space is called a magnetic field. In the next minutes, we will follow that field from atoms to machines.
Compasses, speakers, MRI scanners, motors, and maglev trains all use the same idea. So the real mystery is not what magnets do, it is where the field comes from.
A magnetic field is an invisible map around the magnet. Every point in that map has a direction and a strength. A compass needle is just a tiny magnet, so it turns to match the local field. Iron filings reveal the shape because each tiny piece becomes a little temporary magnet. Where the pattern is crowded, the magnetic effect is stronger. Near the poles, the field is usually strongest, and the motion becomes dramatic. Field lines are not physical strings. They are a drawing that predicts force. Once you can read the field, the rest of magnetism becomes much easier. A magnet always has two poles, north and south. Opposite poles attract because their fields connect smoothly through space. Same poles repel because the field pattern pushes the magnets apart.
This is why magnets can snap together or fight your hand. But the poles are not separate objects hidden at the ends.
If you cut a bar magnet in half, each half becomes a smaller magnet. North and south come as a pair in every ordinary magnet we use.
The bigger question is how matter creates that pair in the first place.
To find the source, we have to zoom into matter. Atoms contain electric charges, and moving charge is one of the roots of magnetism. Electrons have magnetic moments. We can picture them as tiny arrows. In most materials, those arrows point in many directions. When arrows disagree, their magnetic effects cancel. That is why wood, plastic, and glass do not behave like strong magnets. In iron, cobalt, and nickel, groups of arrows can cooperate. When enough of them agree, microscopic magnetism becomes visible. Inside magnetic materials, arrows gather into neighborhoods called domains. Each domain already acts like a tiny magnet with its own north and south. If domains point randomly, their outside effects mostly cancel. A strong magnet has many domains lined up in the same direction. Then their small fields add into one large field around the object. That is what magnetizing means, encouraging domains to agree. Heat or hard shocks can scramble that order again. So a permanent magnet is not magic. It is matter with its tiny arrows organized.
Permanent magnets are only half of the story. Electricity can create magnetism too.
When electric charge moves through a wire, a circular magnetic field wraps around the wire. Bend that wire into a loop, and those circular fields start to stack. Wrap many loops into a coil, and the field becomes much stronger. Add an iron core, and the domains inside the metal help amplify the effect. Now you have an electromagnet, a magnet controlled by current.
Switch it on, the field grows. Switch it off, the field fades. This switchable magnet can do real work.
In a scrapyard crane, current flows through a coil and creates a strong field. Metal pieces nearby become temporary magnets and jump toward the coil.
The crane can lift a pile of steel without hooks or fingers.
When the operator cuts the current, the field collapses. The metal drops because the temporary alignment disappears. This is the practical power of electromagnetism.
A field is invisible, but it can move heavy objects.
The same idea also works on a planetary scale. Earth behaves roughly like a giant magnet with a field around it. A compass needle turns because it is a small magnet inside Earth's field. Deep below us, Moving liquid metal helps generate the planet's magnetism. The field is not perfectly simple, and the magnetic poles slowly wander. But the basic compass idea is still the same. A tiny magnet aligns with a much larger field.
That link connects a classroom compass to the physics of Earth itself.
Now let the field push on a current, and you get a motor. Inside a simple motor, a coil sits between magnetic poles. Current flows through the coil, so the coil feels forces in the magnetic field. One side is pushed one way, and the other side is pushed the opposite way. Those opposite pushes create a twist called torque. Keep switching the current at the right moment, and the coil keeps spinning.
That is how magnetic fields turn electricity into motion you can see. Fans, pumps, toys, and tools all depend on this hidden interaction. But the connection also works backward. If changing current can make magnetism, changing magnetism can make current.
Move a magnet near a coil, and the field through the loop changes. That changing magnetic flux pushes charges around the wire. This effect is called electromagnetic induction. A generator uses induction by spinning magnets or coils again and again. The result is electrical energy flowing out of motion. That is why turbines in wind, water, and steam plants can make electricity.
Motors and generators are the same relationship seen from opposite directions.
Once engineers learned this field language, magnets became technology everywhere. In a speaker, a coil moves a cone, and the cone shakes air into sound. In a Hall sensor, a magnetic field becomes a clear electrical signal. In an MRI scanner, strong fields help turn tiny body signals into images. In a maglev train, controlled magnetic forces lift and guide the train. Hard drives, microphones, transformers, and electric vehicles use the same family of ideas.
The applications look different, but the invisible actor is still the field. A field can push, align, sense, vibrate, lift, or induce current. Magnetism looks mysterious only because the field is hidden. Reveal the field, and the magic becomes engineering.
Here is the whole model in one clean chain. A magnet changes the space around it. That changed space is the field. Inside matter, tiny magnetic moments can add together or cancel out. Aligned domains create strong permanent magnets. Moving electric charge creates magnetic fields. Changing magnetic fields can create electric current. Those four ideas explain attraction, compasses, motors, generators, and modern devices. So when a magnet jumps toward steel, imagine the hidden field map doing the work.